Welcome back to the third and last video on toroids for now. This is Larry Benko, W0QE, and I wanted a lot of wire on toroids recently for the previous two videos. I thought that if I added a few new toroids, a video showing the effects due to various ways of winding the cores would be interesting. So let's get started. For the first test, I took a T106-2 core, which has permeability of 10, and these are the dimensions of the core. And I want 8 turns of number 18 wire on it. Number 18 wire is 1.02 millimeters in diameter. And according to the formulas for the core from the data sheets, 0.864 microhenries was the estimated inductance. And I wanted the core like this to start with, using about 80% of the core. Then I squeezed the turns together to get 50%. I squeezed them together till they were just about touching on the inside here and used 25% of the core. And here I spread them out to use 100% of the core. And the goal being to look at the differences in the performance of the core for those 4 configurations. I captured the data on the 4170, and to keep from having to wait for it to scan each time, I did this in advance. If we load the 25% case, we see inductance of around 1.67 microhenries here. Reasonable Q. We see a resonant frequency of 114 megahertz. Now if we overlay this graph, and this graph represents this configuration right here. If we overlay this graph with one with circles on it, this is bugging the 4170, it always loads this window on a different monitor. Bring the 50% case up. And what we see is quite a bit lower inductance. The inductance here is 1.15 microhenries, 1.16, something like that. So it dropped from 1.6 to 1.16, which is a pretty big change using 50% of the core. The Q looks to be higher than it did before, although the Q curves start to overlap each other pretty badly. And the resonant frequency rose quite a bit. It rose up here to 133 megahertz. So this is clearly a better inductor than this is. Now let's load. I usually wind inductors somewhere around 80%, 75 to 85%. And let's see what that looks like. And let's do that with a wide line because that's the one I think is going to be the best. Now we have resonant frequency. It's just about 140 megahertz. The inductance dropped again. This time it dropped to like 1.02 or 1.03 microhenries. As you spread the turns out, you'd expect the inductance to drop. Although the inductance dropping from here to here was quite a bit. From here to here was much less change. And it's hard to say, but the Q is higher here also. I do that by looking at these in a different format, and I can do that in just a minute. Then the last one let's load is the 100% case. Let's do that with, say, squares. And coincidentally, it produces less inductance, which you realize it might produce less inductance. It also produces a higher resonant frequency, telling me that these 2 turns, the first and last turn, don't get close enough together that the capacitance between them has much effect on anything, which I found that to be a little bit interesting. But what we see here is we see a case where if we were to physically want to mount these, this mounts with the, well, you mount it this way, you can bring the turns down this way. If you bring the turns down this way, you have to add the extra inductance for the wire. And if you bring them this way, the path is a little shorter to mount, but the turns sit against a piece of circuit board or however you're mounting them, which isn't optimal. This way is a pretty good mounting. This way is good mounting. This way is very bad to mount on a circuit board because you can roll this way or this way because these 2 turns are lined up. And this is not nearly as secure of a mounting. So now let's load. I have these shown also in a SimSmith file, which has exactly the same Same thing as I showed before with the 4170 graph, but now we can look at just the Qs. So if we turn these Qs off for a moment, we see the inductance being 1.66 microhenries for the 25% case. We see it dropping to 1.14 for the 50% case. We see it dropping to 1.02 for the 80% of using 80% of the core, and it dropped down to 0.98 for using the 100% of the core. We see the inductance rise as you'd expect to see it rise before we go into through the parallel resonant frequency. And if we look at the Q, so if we call the 80% Q the standard, the 100% using 100% of the windings shows the Q, in my opinion, to be maybe a little bit higher than the 80% Q, not much. The 4170's got a lot of noise here, and if you realize what's going on, you're trying to measure an impedance that's incredibly tough to measure. You're measuring an impedance that's got a reflection coefficient that's 0.99, maybe even 0.999, and it's just hard to do that accurately. But we do see when the Qs get lower, like 60%, that looks to be a little bit lower, maybe, not much. 25% is just different. It's hard to say. None of these have bad Qs. But so I wouldn't use Q as a measurement for whether the inductor is better or worse. I would use, in this case, I would probably use which one is easiest to mount. And if that's the case, I would use this one or this one. And as far as needing a little more inductance or a little less inductance, when you only have 8 turns, you're probably going to end up spreading them or shrinking them, squeezing them together to adjust the inductance, because one more turn is a lot of inductance change. So anyways, this is one example. Now let's take this example and do something else with it. Let's now look at the same core that we had here for the 80% case. It's shown in 4170 right now. Let's do a quick scan of that. And we see what we saw before, resonant frequency just above 140 megahertz, and we see it being 1.02 microhenries. And now let's assume we're going to mount this on a circuit board and we're going to lay it down flat. We can mount it on a circuit board like this, which is how I normally would do it, which changes things just ever so, almost imperceptibly. But let's mount it this way on a circuit board. And this is just a piece of FR4 circuit board, and I'm just going to lay it on there. And let's look and see what the changes are when we do that. We definitely see that the Q's lower. We see the resonant frequency dropping to 135 megahertz. And that's pretty much it. The inductance did not change much at all. So if you're willing to tolerate a modest, not a huge decrease in Q, the Q changes very little where the Q is not very high, but the Q changes a lot more where it's high. Again, whether you trust the 4170 or not, I don't know. I don't think its accuracy is that good. Now let's mount this on a circuit board again, but this circuit board, we're going to mount it on the FR4 side, but it's got ground plane in the back. Let's see what the effect of that is. Again, the Q's been lowered. We're seeing that the inductance is rising sooner, which means the resonant frequency is going to drop. It did. The resonant frequency is down below 125 megahertz now. And finally, let's mount it this way. We could if we wanted to. You'd be foolish to do that if there was very much voltage involved. But for a very low voltage application, you could certainly do that. And rescan once again. Again, the Q looks like it's a little bit lower. It's hard to say. It hasn't dropped massively, though. The Q hasn't. But the resonant frequency is certainly changing a lot. So here we are. The inductance didn't change very much. Q's dropped somewhat. Resonant frequency's gone from 140 megahertz down to about 115. And for the last thing, if we put a piece of closed cell foam on here, we should see almost no change at all. So let me do a rescan of that. It should line up and come through the resonant point at just a little bit over 140 megahertz. We see it maybe is just, the lines are both almost exactly on top of each other there, but it's dropped a little bit. Now, if I put my finger on there, we will see, even though it's only on this side, we will see it dropping more. Now the resonant frequency dropped to about, I don't know, 136 megahertz. Again, not much. And finally, let me just put my finger right on the turns. We'll see a big change there. We see the Q is destroyed in this inductor. Resonant frequency went down to below 90 megahertz. So clearly, a toroid is not totally shielded. And this is important if you want to do much with them in terms of having several of them together. This piece of foam core material is pretty much air, and it's a 1/4 inch thick, and it had almost insignificant effect. So, draw your own conclusions as you wish to this, but it's interesting that the effect is definitely noticeable. Let's move on to another example. For this example, I took a smaller core, number 6 material, permeability of 8, and I wound a lot more turns on it, 37 turns of 26 gauge wire, which is 0.40 millimeters in diameter, and the estimated value according to the formulas was 6.16 microhenries. When I pinched the turns together completely, they occupied just a little over half the core, 55%. I spread them out a little bit, and at that point there was almost no gap between on the inside here between the turns. Then I spread them out to a little bit more, so there's just a teeny bit of gap, 60%, then 80%, then 100%. And finally, I unwound 2 turns. I put them 100% of the way around, and then the next 2 turns I interleaved the turns on the other side. So turns, if the turns were numbered 1 through 37, turns 36 and 37 would be interleaved between turns 1 and 2 and turns 2 and 3. And that's just how I wound them. And rather than go through the 4170 plots like I did before, I took those files from the 4170, I imported them into SimSmith, and I let SimSmith do the work. In SimSmith, I'm doing plotting similar to what I've done before, where I plot the magnitude of things. And if people are interested in this kind of stuff, that can be a video on itself. You can pause this video and look at that if you wish to. Also, see what the format is. Just pause the video. But if you want to, in the essence, with the idea to try to keep this moving along, let's look at what's going on here. At 55% of the turns coverage, we have an inductance that's 8.66 microhenries. At 60% of the turns coverage, which really wasn't spread out very much at all, we drop that drops down to 7.75. 80% drops down again to 6.69. 100%, it drops down a little bit more, 6.2. And at 100 turns, with 2 of them overlapped, it actually rose a little bit. And we see the effect of those 2 extra turns that overlap the turns from the other end of the core coil, with a huge reduction in the resonant frequency. So the resonant frequency for the highest resonant frequency is the 80% case, and that's pretty expected. In this case, the 100% case, the resonant frequency dropped. The 100% case, it dropped quite a bit to here, and this is what we got. Now let's look at Q for a moment. Again, thinking that 80% is the best Q, that's what the 4170 tells us. Then I looked at the 60% Q, and it's less. The 55% coverage Q, dropped even lower. Those are all reasonable. Then I looked at the 100% Q, and it's higher. And I really never thought that was true. So either I've missed something along the way, or something else is going on. If I look at the 100% Q with the two turns interleaved, it's less than 100%, and that's to be expected. It also has this nastiness that occurs out here after it becomes a capacitor. I don't want to read into that particularly, but anyways, I had returned the HPQ meter prior to doing these tests, and this was kind of bothering me, so I called my friend Tom, W0IVJ, who I borrowed the 4342 Q meter from, and asked him if he'd make this measurement, and he did. And he came up with, and his results were these measurements. And what we see is, at 50, he did 50% instead of 55 and 60, but at 50%, 80%, 100%, we see a slight increase from 80% to 100%. You could almost say that this is imperceptible. But from 100% to 100% plus two turns, we did see a drop. And I had always been told and always thought that the 80%, 85% range was the highest Q. It appears to not be the highest Q. However, when we get to 100% of the turns, we start to enter this territory where if you were to wind the core and I was to wind the core, my 100% might be a little closer than your 100%, and yours might be a little closer than mine, etc. And there's quite a bit of variability there. At the 80% point, the variability is much less. I'm still a fan of winding them at 80 or 85%. Plus, the mounting is not to be diminished. So if we look at the mounting again, both this mounting are extremely fragile if you mount them on a circuit board. This mounting does not lend itself easily to a circuit board unless you put longer leads on it or you lay it flat. The 70 to 90% range leads you to the best mounting, and it gives you something that's actually a little bit stronger. So when you put the circuit board on this side right here, you mount these leads through the circuit board, you end up with some stability in both dimensions. And that's what I typically do when I do it. But this is another example, and it was kind of surprising to learn something that the Q at 100% of the turns actually is a little bit higher than the Q at 80% of the core being covered with the turns. And in this example, we'll look at winding some common mode chokes. Common mode chokes are primarily used in the reduction or elimination of EMI and RFI interference. And the typical material that's most commonly used these days is number 31 material, which has a permeability of 1500. I did this little table based on some common cores that you might use in this application. The first one is the standard core that's 2.4 inches outside diameter, 1.4 inside, half-inch height, right up here. It's a fairly expensive core. It's used all the time. It's large enough inside diameter that you can wind turns through there that may have a plug on the end. Although if you get very many turns in there, no longer can a plug fit, or a connector at the end of a wire. But this is the go-to winding for a lot of people. And this can be wound in both a conventional manner like this, or it can be wound in a crossover manner, which I'll show later. But there's a certain number of turns here that will give you an optimal value. And you can also wind your wire through split toroids like these, or solid toroids like these. In this case, these would have to have a connector put on later. But nevertheless, let's just look at these very quickly. The core here has dimensions like I mentioned. And in the previous video I calculated effective factor for the core in terms of creating impedance. And it basically is A sub E, which is the aperture of the core, which is you do a cross-sectional area of the core. That's that area divided by the mean magnetic path length. So if we do this calculation, in this calculation right here, this is the only number that's important. This core has a factor of 0.1. These small beads have a factor of 0.3, roughly. So they are 3 times as good at creating impedance as this is. This is worse. Now you can put more turns on this core than you can on these. And if I set the basis as being 1,000 ohms of impedance at roughly 1.8 megahertz, and that turns out to be about 90 microhenries. I calculated for 90 microhenries on all these, and I did the closest I could get with the number of turns. And it took 7 turns on this core to get that. It took 4 turns on these cores to get the same thing. So that's the only purpose of this slide, is to show that we need more turns on this core than we do on these cores, but these cores are cheaper. Maybe they're less convenient to wind. It's, it's your call. And here's the current prices from Mauser. These were not listed in Mauser. These are available from lots of people, though, these cores. DigiKey, Arrow. I buy cores from Arrow all the time. They generally have pretty good price on cores. But this is where this sets the stage for what kind of core you'd like to use. Now let's look at 3 cases with different number of turns on a 2.4-inch outside diameter core, number 31 material, and see what the impedance is. And rather than putting you through the scanning process, let me just load the files. Shown here is the file for the top case, which is 6 turns. And with 6 turns, what we see is we see an impedance at 1.8 megahertz that's a little bit less than 1,000 ohms. We said we needed 7 turns, and this is 6 turns, so that's a pretty reasonable guess for the number of turns. We see it become inductive, and not become inductive. It is inductive up until about 23 megahertz, and then it becomes capacitive at that point in time. The interesting thing we see is if we move this scale back here again to, it's a little tricky to get the adjustment here. From 1.8 megahertz, we see a Q of, the Q here runs from 0 to 20. So here's a Q of 1 right here. So we see a Q of roughly a little bit over 1 at 1.8 megahertz. And that in the impedance of this 6-turn core has a Q of less than 1 all the way up through 50 megahertz. Now this is due to the fact that the 31 material is incredibly lossy material. And if you were to foolishly decide to wind an inductor on this core material, you'd find out that the inductor would be a terrible inductor because the Q is so low. However, for reducing EMI interference, this is exactly what we want. The resistance is our friend at this point in time. But we see that this curve peaks at around 30 megahertz, and maybe we wanted a little bit more impedance at the low frequencies. So let's see what happens if we overlay this graph with one with 8 turns. Now here we have the 8-turn winding, which is shown here. And what we see is more impedance again. So now we see impedance somewhere in the order of around 1,500 ohms at 1.8 megahertz. And we see it peaking somewhere in the order of slightly less than 20 megahertz. It peaks. It has more impedance than the 6-turn winding did at all frequencies up to 40 megahertz, which is good if you want this for lower frequencies. And the Q is still pretty low. It's Q's low, Q of 1 at 1.8 megahertz. Q is 1 at 30 megahertz, and it rises a little bit more beyond that. But again, Q of 1 is incredibly low. So now let's overlay the graph with the with 11 turns that I did here. Okay, here's the curve with 11 turns. Again, we see a shift lower in the peak impedance in frequency. The shift goes lower again. This 11-turn winding is inductive only up through about maybe 7 megahertz or so, where it becomes capacitive. But nevertheless, it has a low Q from Q of 1 or less from 0 to 20 megahertz, and the Q rises to a little bit less than 2 at 30 megahertz. So if you were having problems at interference problems at lower frequencies, this would be a better choice. And one other thing to consider is people also mention, well, it's better if you do a crossover winding. And a crossover winding, let me overlay that with squares. Okay, that was an 8-turn crossover winding, and the 8-turn crossover winding lined up very closely with the curve that was the wider line curve, which was the 8-turn standard winding. However, the crossover one had a little bit higher Q. No, it doesn't. It's almost exactly the same Q as the standard winding, saying that there's very little difference between the two in terms of performance. Whether you like to wind one way or the other way, that's kind of your choice. It seemed to me that if you're concerned about the higher HF range, you're better off with 6 turns. Lower HF range, 11 turns, somewhat over the whole band. 8 turns seems like the good choice. And these are incredibly high impedances. 2,500. This is 3,000 ohm peak right here, and this is 4,400 ohms, which is incredible and almost impossible to achieve, as we'll see in a moment. And in this slide, we have shown in the wide trace the exact same curve we saw previously, which was the 8-turn winding. And we saw the impedance being slightly over 3,000 ohms at just a little bit below 20 megahertz. I took that same core and I moved the analyzer down onto the table, and I extended the wires about half an inch is all I had to extend them, and I laid this flat against the table. Laying it flat against the table reduced the impedance to this number right here. So we saw a reduction in frequency where it became capacitive, and we saw a peak reduction in the actual impedance. Anytime you try to get these impedances very, very high, it's extremely difficult to do that if the core ends up touching anything at all. I mean, you think about what 3,000 ohms of impedance or 5,000 ohms of impedance at 30 megahertz is about 1 picofarad is equivalent to what this thing represents, 1 picofarad of capacitance. And being near just about anything reduces its effectiveness. So that's something to be concerned about. And if you wind for this incredibly high impedance and you measure it on an analyzer and you put it in a circuit and you lay it down on a table, lay it down behind equipment, other wires are nearby, you will see a lesser performance than you would have seen otherwise. Now, it turns out that the impedance reduction you see is less if the core has less impedance. What that means basically is if the core isn't very good, it doesn't get hurt much by putting it on a table. A metal table is even worse. But this is something to definitely be concerned about. And here are shown 4 graphs with beads. The bead typically has a higher effective value to create impedance, but has a smaller opening. And since the opening is smaller, that means the turns are going to be much closer to each other than they would be in a larger core. And I tried to understand whether or not trying to separate the starting turn from the beginning turn from the last turn is important or not. So I built this little polyethylene insert that fit inside a core and could separate the turns and keep them spaced apart or not, or keep them together if they were in this slot, and any of the other four openings would keep them apart from the other turn, at least somewhat. I put 6 turns through here, and what's shown in this picture is the starting and stopping turns are adjacent to each other right here. But I could wind this differently. And the top 3 green curves here show the effect of that. And the green curve that has the highest impedance here is the one where the starting turn and the stopping turn were definitely apart from each other. Two of the middle turns were connected here, and the other 2 turns were in here. The worst case one right here was where the starting and stopping turns were adjacent to each other. The effect shows here that it's not terribly important whether the placement is done well or done poorly. So in my opinion here, it's not worth trying to say the starting and stopping turns are far apart. Now, when I wind these things, I usually make an attempt to keep them separate just because it seems like it's a good idea. But the tests show that it really doesn't make much of a difference. Shown also here in a wide graph is the effect of 5 fat turns with larger wire that are put through here, and the 5 turns fill up this area pretty nicely. In this case, the input turn is on the bottom here, and the output turn is up here. I want turn 1, turn 2, turn 3, turn 4, and then left the space at the top. It's probably easier to not do that. The effect is really pretty insignificant, which was interesting. I was thinking it would be a little bit more significant than that, but it doesn't appear to be that significant at all. What is shown here is the importance of having a split core, if you use split cores, be in good physical contact one core to the other. What I've done here is, there'll be 3 graphs here in a minute, but right now there's just 2. The solid line without the circles represents a new split core with 3 turns of approximately 1/4 inch diameter wire that does fit inside the center of these cores, but it's pretty tight. And I've smashed it down, and I get this impedance, the solid curve. Shown in the dotted curve, I put an artificial gap in one side, and this gap would be representative of snapping a core on wire that the wire is pushing against the plastic housing. And over time, the plastic housing gives a little bit. The wire wins. I mean, time always wins. And there's a little gap there. This piece of paper was 4/1000 of an inch thick, and I put it just on one side, and I was able to snap the case around it still. We see a reduction in impedance of about 50% down at the low frequencies. So here's say 10 megahertz. It's just about half the value. Now at high frequencies, is actually higher impedance than if the core was in contact with itself. But at lower frequencies, we lose a huge amount by having this open. And I also plotted one more. And that curve is the one with the cable ties around it. So we can see that when this core is new, the plastic housing was strong enough to beat any pressure that the wire had trying to open it up. But over time, it might open. And I've had some experiences with that. I had a friend who came over to my house one day. He had some problems with the mobile radio in his car, and he had interference with the remote head unit. And we fixed it, and he called me up about 6 months later and said he had a problem again. And what had happened was, in his hot car, the wire that he had wound inside the split core had pushed the core apart just a little bit. I asked him to look in there, and he said there's no gap. But then I asked him to put some cable ties around the outside, and he put the cable ties around the outside, and everything worked again. So what this shows us is the fact that these cores, while they're really nice to use, if you put a lot of wire in them, or if the wire is pretty stout wire, over time the wire may open up the core a little bit, open up the plastic housing that's holding the core in contact with the other side of the core, and the impedance will drop pretty drastically. So here I have the 4170 in the recycle mode, where it's just scanning over and over and over again, and it's scanning the homemade binocular core that I used in the previous example. And we see that the peak impedance is somewhere like 3,300 ohms, 3,200 ohms, something like that, occurring at about 14 megahertz. Now, if I get near this circuit and put my hand, say, on it and touch it, I'm squeezing the core right now, not touching the turns at all, we can see that the impedance drops significantly. And if I let go again, of course, it rises. Now the difference here, due to my body, the capacitance of my body, and the fact that these are incredibly high impedances, means that you probably won't be able to achieve these kinds of numbers unless you spend some serious effort trying to isolate this core from whatever, such as putting it on some kind of a pad that has pretty much basically air in it. These kind of like they're kind of like a high-density foam. They work pretty nicely, or something else. But if you let this core sit on a table or a desk, or sit next to other wires, you will not be able to achieve the value you measure. That's probably all I've got about to say about this topic. I hope this has been interesting. There's been a lot of information here today, and this is a pretty interesting topic to me. If you found this interesting, please give me a like, thumbs up, those kinds of things. Subscribe if you haven't subscribed to the channel already. The more likes I get, the more subscriptions I get, the more comments that get made to the channel, the more likely YouTube is to recommend this video to someone else who's never seen who has never seen anything from my channel before. So if you'd like to help me out, that's the best way to do it. I appreciate it. Thank you again.